Hello, everyone. Thanks for joining us today for our AMS webinar series. And it looks like we have a number of new users attending, so thank you for being here with us. So we're going to start out by just going over the typical workflow that you would take when you start any CAM job with our MecSoft CAM products. We're going to start up in the top left corner, and obviously you're going to load your part and you're going to define your stock geometry, not mentioned, but also you define your setup, everything that you need to start programming the part. So if we take the arrow to the right, the very top, we see three balloons in the middle. Create roughing operations, create pre-finishing operations, and create finishing operations. Now, depending on your part, what you need to do, you may not need a pre-finishing, you may just need a finishing. So, but this is an idea of the process that you're going to take. Now, if you move to the right, the far right, you see simulate material removal. And you see that arrow goes to the left and the right. So anytime you create a new operation, you want to simulate it so you get an understanding of where that tool is going to go, how it's going to cut. And you want to do that every time, like I mentioned, every time you make an edit, but also every time you add another operation, because for instance, a second operation will be based on the cut material simulation of the first. So you need to do a complete simulation of all of your operations to get a clear understanding. And there's some users who they get comfortable using the product and they decide that they don't need to do a simulation. Well, I'm going to tell you, you need to do one every single time. Even if you understand what's going to happen and it's not really complicated, it will highlight areas that you may not have thought about, and it'll protect you from possibly damaging a tool or some stock. Now, we'll talk very briefly about the machine and the setup. We've got two graphics here. The one on the left shows the default setup when you run the product. So when you run the product, you'll see that you have one setup defined in a machining job called setup one. That setup, the orientation, meaning the X, Y, and Z axes, by default are aligned with your world origin in the CAD system. So by default, the X is to the right, the Y is looking into the machine, and the Z obviously is pointing up to the machine spindle. So for the express, standard, expert configurations, this is the setup you're going to see, and you can't change that in those configurations. You have one setup, and if you need to move your part around, then obviously you can't move the setup, so you have to move your part if you need to orient it properly or a different way than you want to. So on the right, in addition to defining a setup that matches the coordinate system of your machine, you can also add what we call work zero. So by default, when you open up a new drawing or model to machine, like I said, the setup one is aligned with the world origin. Also, that becomes the zero origin location to calculate your tool paths. You can move that origin, okay? Even in the standard, in the early configuration, you can move that origin by creating a work zero and put that work zero underneath your setup one, and you can define where that work zero is, whether it's at the top of your stock, bottom of your stock, however you want to locate that work zero, and then that work zero will then become the coordinate origin for all tool paths. Okay, let's talk a little bit about geometry. In our CAM products, you can program tool paths with just lines and curves. Like you may have a wireframe drawing. Typically, wireframe drawings are not used much anymore. But if you had just a 2D drawing, top view of a part that you needed to machine, you could use that in conjunction with 2.5 axis toolpath methods to machine your part. If you're going to work in 3 axis, you do need to have a part model. You need to at least have a surface. Okay, it doesn't have to be a solid. You can machine just a single surface in 3 axis. Typically, though, you'll have a poly surface or a group of surfaces, or a closed poly surface, which is actually a solid model. So you can use solid models, open poly surfaces, etc. for 3 axis. Now, the bottom left part, you can use 2.5 axis methods on a 3D solid as well. So on the far right, you see a mesh object. These are produced by point clouds, which in turn are produced typically by a scanning device for scanning a part that you want to reverse engineer back into the CAD system. And you can also machine these faceted mesh data with 3 axis methods. Now, let's talk a little bit about the difference between 2.5 axis and 3 axis. Basically, it's defined in how the tool moves. If you look on the left side, you'll see that the tool, we have a red arrow X and a Y arrow Y, I mean a green arrow Y. The tool can move in these 2 axes simultaneously, but it's fixed in its Z axis. So you define the depth of the tool to cut, and it will stay fixed at that depth and move in X and Y. So, and the movement in X and Y will be contained by the control geometry that you select. Now in 3 axis, you see that we have a third Z axis in blue. So in 3 axis, the tool can move in the X and the Y and the Z simultaneously. It may not be moving in the Z at all times, and it may not be moving in either the X or the Y at all times, but it will and can move in all 3 directions as needed at the same time. So that's just real basic understanding of the difference, how the tool moves in both 2 axis and 3 axis. And if you look on the right also, you see a boundary curve at the base of that part. You can contain your 3 axis operations to the control geometry that you select. So basically the underlying part in 3 axis is controlling the tool, because it won't gouge the part. It'll use that part as a guide to cut over it. Now let's start out by talking some basics about 2.5 axis machining. What you see here on the screen is the XY view of a part, 4 different parts, and you see the red dots are the tool diameter looking down on the XY plane. So what we're trying to convey here is we want you to understand how that tool is going to behave when it reaches, or when it is controlled by the control geometry that you select. So on the far left, in a facing operation, the tool center point of the tool will stop on the control geometry. So it's going to cut right up to the edge of the control geometry, and your tool is going to stop on the control geometry itself. If you look at the second from the left, you'll see a pocketing operation, and the tool diameter of the tool will stop when it makes contact with your control geometry. And you also, in both in the facing and the pocketing, you have a offset distance that you specify also, which will be used to offset the tool and clear either a face, top face, or a pocket. Now, if you move to the right for profiling, the contact points is identical for pocketing, except that you're not clearing out all of the material inside. You're probably assuming that you've already cleared it out to some extent, or maybe used a pocketing operation and left some stock on the sidewalls. So you're going to use a profiling operation to finish the sidewalls and maybe even the depth of the pocket. Now, all the way to the right, which is a very versatile operation, you really should get to know your engraving operation. In engraving, the center and the tip of the tool will follow your control geometry wherever it goes. If that control geometry is tapered on, it's a 3D curve, you can use the 2.5 axis engraving to follow that curve. It'll follow it wherever it goes. So that's a good operation if you want to engrave some lettering on a part, or if you want to tell exactly where you want that that tool to move, you can just draw the control geometry curves, and you can use that as input to your engraving operation. Now, this is the basic, the 4 basic operations. There are more advanced operations in in 2.5 axis, but we're just touching the basic operations.
I'll add a quick note here, Don.
Yeah.
One of the things that the way you can think about facing and pocketing is you can think of facing as you're machining cores. And then if you're from the mold making world, you can think of facing as the outer boundary actually represents the outer air to be machined, so the stock to be machined, so you can approach the part from outside. So it's really a core type of machining operation. While pocketing, you're machining a cavity where you cannot enter from the outside. It's enclosed on all sides, so you'll have to enter inside of the perimeter of the control geometry. So if you're oriented that way, that might make it easier to think about facing and pocketing in that fashion. Thanks, Don.
Okay. Now here is just an isometric view of each of those examples. As Joe mentioned, if you start on the facing on the far left, you'll see that the control geometry extends out to the perimeter of the part to clear the entire face. And for facing, obviously, you can use flat end mills and facing mills, etc. Again, the pocketing, obviously, we talked about that. The flat mill is extending till it touches the control geometry at the perimeter of the pocket. And the same with the profiling. And then the engraving operation on the right, I showed a round slot. You don't have to have any geometry other than a curve for that tool to follow. I just showed a slot just to give it a representation of cutting around that control geometry. In this case, simplified case, just creating a rounded slot. Now let's talk a little bit about, you're going to want to understand how the tool is going to cut, how it's going to start cutting, and what side of your control geometry is going to be cut. Because you have different options in the cut parameters tabs of the 2.5 axis operation types to tell right side, left side, inside, outside, etc. Just so you understand what right and left means, if you look at the top left illustration, you'll see that we have just one line, one curve, starting at the bottom and continuing to the top. If you see the little squares there on those geometries, those are the start points. That is, anytime you draw a line or a curve, by definition, it already has a start point. If you draw a line from point A to point B, point A will be the start point as defined by the CAD system. So if you machine on that line, the start point is where the tool is going to start cutting. And the right hand or left hand, obviously, if you're standing at the start point and looking down the curve, right side is your right side, obviously, and left is your left side. And that's also the case in closed curves. If you have a circle has a start point and it has a direction. So if you're going to want to machine the outside, that would be the right side of the circle in this case. If you go on machine on the inside, that could be the left side or the inside. And
quick note on this slide actually applies mostly to the profiling machining operation. Because the curve direction on the right side and the left side all come into play only in profiling. As we mentioned, in facing and pocketing, the curve determines, the closed curve determines the side, because in pocket it's always on the inside, and on the facing it's always on the perimeter. Right. So we're really talking about the profiling machining operation here. It's important to know.
Thanks, Joe. Also, just on an open NURBS curve is the same. You have a start point and you have a right and a left. If you look down below that, you see using multiple curves. On the left, you see we have 1, 2, 3, 4, 5, 6, 7, 8 curves that are closed, but they're not merged into one single curve. So you see start points at each of the curves. We highly recommend that if you're going to machine more than one curve, is that you merge that into a single curve. And if you're on the right, you'll see that it has a merged curve has one start point and it's closed continuously. So that is the method you really want to strive for if you're going to do any curve machining. Obviously it's more than one curve. So always remember to join your curves or merge them together. And then on the right, we just see the different indicators of the start points and directions of curves. So basically, understand here in profiling, the tool is going to start at the start of the curve. It's going to cut on the side of the curve that you specify, right side, left side for an open curve, inside, outside for a closed curve. Now let's talk about a basic understanding of cut levels in 2 axes. You may have seen, if you look at this dialog on the right, you probably have seen this dialog, and it may be a little intimidating at first. But once you understand what it's doing, you'll see that you have absolute control of the depths of your cuts. So at the top of that dialog, you have location of cut geometry. Now, just ask yourself, the control geometry that I selected, where is it in relation to the depth of the cut? Okay, is my control geometry at the top of the cut, like on the top right image? Is the control geometry at the bottom of the cut, like in this image here? Or if your control geometry is not on the top or the bottom, or if you want to specify a different top position to start cutting, you can use the pick top. Now, you can use the pick top, and just one basic example, if you want to face off your spool board and you want to cut below your typical bottom of your part as it sets on the spool board, you can use the pick top, and you can define the top where it's going to cut, and you can give it a depth, and that depth may extend down past the bottom of your part, and that's where the cut levels will end. One thing to note, if you use the at bottom, the tool will not go past your control geometry. That's where it's going to stop. So it's going to start, it's going to work its way back for the total cut depth. If you end at the bottom, it's going to calculate upward your total cut depth and start cutting there, and then cut your rough depth per cut at each level. Now, a little bit more about this dialog on the right. If you look at that illustration, the dialog icon, it tells you how this is working. So you got the location of your cut geometry. In this example, it's at bottom, okay? And for the total cut depth, it's 3/4 of an inch. So if you look at the total cut depth on the left side of this illustration, the total cut depth starts or ends at the bottom of the control geometry, and it starts, the total cut depth works its way up and starts there and works its way down. Now, the rough depth per cut and the finished depth, you can break this total cut depth into two parts, a rough depth area and a finished depth area. Now in the picture here, you see the light blue or cyan lines. That is the finished depth. The dark blue lines is the rough depth. So you can tell it with these two sliders down below, what is my cut level for the rough depth area and what is my cut levels for the finished depth area. So that's just some basic, and you'll see these options on virtually every 2.5 axis toolpath dialog. Now let's talk about how basic tools interact with your control geometry. And this is very critical that you understand how these three tool types are going to act. So typically for 2-axis, you'll use a flat end mill, cutting pockets or cutting profiles, or facing. You can use a flat end mill for facing. In the image here, you'll see that the diameter of the tool stops at the side wall of the control geometry where the little square is, okay? The red dot is the program point for the tool path, and you'll see that the blue lines extend out, stop at the center of the tool, and each one of these are cut levels down to the bottom. That's a typical basic 2.5 axis pocket. Now the middle image, you can use tapered tools in 2.5 axis. If you have a chamfer on an edge that you want to cut, you can use a tapered tool. What's going to happen here is that the taper of the tool is actually the flute length, okay? And the taper is going to come over and stop at the perimeter of your control geometry. So the deeper the taper tool goes down, the earlier it's going to stop. So you can see the red dot, and then it slants to the left all the way down. So at the bottom of the pocket, the center of the tool would be here. So you can use that obviously to cut chamfers. Also, you can use it to cut drafted walls. If you have a constant draft on a wall and you have a taper tool to match that angle, you can use that to machine that draft. Now let's look at the one on the right. It's important that you understand how a ball mill is going to act in 2 axis. The tip of the tool will stop on the perimeter of your control geometry. As you can see, we stop the tool at the very first cut level, and you'll see that the arc radius of the tool touches the control geometry. This typically is not what you want to do, especially if you're machining molds. Obviously, if this area right here was a parting line, you don't want that cutter to ride that parting line because it's going to cut that edge at 1, 2, 3, 4, 5, 6, 7 levels. That tool is going to recut that edge 7 times, and you're going to have tolerance builds up. You're going to have just a sloppy edge right there. So typically you won't use a round ball mill for a pocket. Now for profiling, if you're just going to cut at the bottom of the pocket, if you want to leave a profile in your part, you can use a ball mill and just run it at the bottom of the pocket around. And actually our part that we're going to demo actually uses a corner radius mill that incorporates the radius into the part, and I'll show you that. So these are the basic understandings. Go ahead, Joe.
Yeah, quick note on the ball and mill. Actually, 2 notes. What we're looking at here in the profile that Don has just shown, we call this the waterfall effect. So you can think of it as the tool is contacting that edge and it's waterfalling over that edge. And the middle picture, we call that the chamfer effect. Again, the same thing. It's contacting the side of the tool, and you're seeing that chamfer. One important note: a lot of new users get caught up on this. I just wanted to mention, if you're using a ball and mill and you select the curve as your machining geometry, as Don is showing here, but did not specify any cut depth, then you're going to get one cut level, which will be right on the same level as that curve if you have selected a big top. So, but if you're using a ball and mill, this red dot is actually going to be right on that curve. So you're not going to get any offset at all. And this kind of throws a lot of new users. They're saying, why am I not getting an offset? The reason you're not getting that offset is because the contact point of a ball end mill on the control geometry is right on it at that particular cut level. So that's something important to watch out for. Thanks, Don.
Thanks, Joe. And again, if anyone has questions, go ahead and add them. I see we got a few questions. That's great. We'll get to them here shortly. Okay, let's move right along. Let's talk about cut our stock allowances in 2.5 axis. In 2.5 axis, the stock is measured on the side of the tool, the side walls of the part. So we got in this dialog on the left, we got 0.1 for stock. That 0.1 is measured on the side walls of the tool. And if you look in the illustration on the top right, you'll see the stock remaining is extending in the X and the Y direction of the part. So that's basically an understanding. Remember that stock is not automatically applied to the bottom of the tool on the bottom of a pocket. You control that with your cut levels. So the slide previous.